So welcome to you all to my presentation here. So it's really an honor for me to give this presentation here and to be invited for this at the place where I did many years ago my PhD. So today I would like to report to you on what I did and what I still do. So what I did during the last 10 years and still doing, and would like to give you an overview of the POD service and also try to answer the question, what is the connection to the IGS of this Copernicus POD service. And first of all, I would also like to acknowledge the Copernicus POD service team, because without them, this presentation would not be as it is. So, for the outline of the presentation, so first of all, giving an introduction to the Copernicus program and the Copernicus POD service, because I think many of you do not know what exactly it is. Some of you, of course, know it already. And then answering or trying to answer the question, what is the connection to the IGS? I also have formulated a bit different, so where are the connections between the IGS and the Copernicus POD service? And I would like to underline this with examples and results from the POD service. Then giving a short summary, and at the end I will also provide some information about the future of the Copernicus satellites. So first of all, to Copernicus. So Copernicus is the European Union's Earth observation program, looking at our planet and its environment to benefit all European citizens. So it's a nice sentence to explain this. So it's a program which is set up by the European Commission, ESA, EUMETSAT and others, and consists of several services around the topics of atmosphere, marine, land, climate change, security, emergency. And the Copernicus program consists of several Sentinel satellites. So we have here in the bottom row Sentinel 1, 2, 3 and 6, which are the ones which I will talk about in the next 40 minutes. And then we have as well Sentinel 4 and 5, which are in the box on the very right, but they are also Copernicus satellites, but I will not tell anything about them today. So we have Sentinel 1, 2 and 3, which are all in polar orbits, so near polar orbits with 98.6 or 7 degrees. And they have different heights, so the lowest one is Sentinel 1, close to 700 kilometers, then about 100 kilometers higher, Sentinel 2, and then Sentinel 3 even a bit higher. They have different purposes, from synthetic aperture radar for Sentinel 1, and multispectral imager, and then the altimeter satellite, Sentinel 3 and Sentinel 6. So Sentinel 6 is the successor of the JSON series, which I think also many of you know. And it is now the reference altimeter mission. And you see for POD, so precise orbit determination, we have on all satellites GNSS receivers, and for Sentinel 3 and Sentinel 6 we also have a DORIS receiver and laser retroreflector for satellite laser ranging. And just for giving you information who's operating the satellites, so Sentinel 1 and 2 are operated by ESA. Sentinel 3 is a joint operation between ESA and EUMETSAT, and Sentinel 6 is then operated by EUMETSAT. Okay, some nice pictures which comes out from the Copernicus services and also connected scientific work and research. So first of all, on the top left you see some detection of methane anomalies, and this is really a joint work between, or joint finding from Sentinel 5, 2 and 3, so all these 3 satellites contributed to this study. Then on the bottom left you see a nice picture of a Saharan dust cloud which comes to Europe from time to time, and it's catched by Sentinel 3 in this case. And then on the top right we have a result from monitoring flood in Germany, and on the bottom the very latest, one of the very latest results from the Naples region, so that they detected the strongest uplift since the last 40 years with Sentinel-1. So these are just some examples which you might already have seen in the media or so from these Copernicus services. So coming back to the satellites which are in orbit currently and with which we are working. So we have in total 7 satellites. By now, only 6 of them are still operating. And you see since April 2014, more or less once per year, sometimes twice per year, we have a new satellite launched. I left over the future because I will come to this at the end of the presentation. But you see that we have for Sentinel-1 we still have 1 satellite, 2 we have 2, 3 we have 2, and for Sentinel-6 also 1 satellite in operations. So coming to the POD service. So this is just a summary slide. So we have within this Copernicus program the Copernicus POD service, which is a consortium led by industry, and this consortium is then also together with other institutions building the quality working group. And we have different latencies and accuracy requirements for our orbit programs. And I just want to go into detail in the next slides on all these graphics here. So first of all, on the POD service itself. So since 2014, so now 10 years, the CPOD service is responsible for providing precise orbit and auxiliary data files for the mentioned Copernicus Sentinel-1, 2, 3, and 6 missions. Of course, at first it was only Sentinel-1A, and then all the others came when they were launched to this. And GME, company in Spain, is the provider of the operational part of the service. And they are also doing most of the work for the service. And they are leading the CPOD consortium. And this consortium consists of several institutions, which are listed here, where you can see, for example, Positive, that's myself, and then also other institutions, so DLR, GSAT, TU Delft, and TU Munich. And then together with even other institutions, so CNES, IU, TU Graz, GNSS, JPL, and Goddard Space Flight Center, they are forming the quality working group, and this quality working group is chaired by ESA and co-chaired by EUMETSAT. And these quality working group members, they deliver regularly orbit solutions for all Sentinel satellites to the CPOD service, or to GMV for the quality control of the CPOD orbit products. And this quality working group meets once per year, and we discuss recent developments in LEO POD in general, and also involvements of the CPOD operations. And as this quality working group, we formulate recommendations towards ESA and EUMETSAT regarding current flying satellites, but also future Copernicus and other Earth observation satellites requiring precise orbit determination. And so the GNSS writings files of all these missions and the non-time critical orbits from CPOD, from all missions, as well as the combined orbits. We'll come later to this, what this means, of Sentinel-3 and Sentinel-6. They are provided on the Copernicus data space ecosystem. So they are publicly available and you can download them for your use. And so the CPOD service is also responsible for providing the orbit predictions for Sentinel-3 to support the satellite laser ranging of the satellites. For Sentinel-6, this is done from EUMETSAT. And just in some numbers, so we have 4 missions, Sentinel-1, 2, 3, and 6, 7 satellites, and I know now only 6 satellites, 4 timeliness, so prediction, real-time, short-time critical, and non-time critical, and about 100,000 orbital products per year. And so 8 engineers at GMB are working for the POD service, and yeah, as I said, from the other institutions also, some other persons are working for the POD service. So coming to the different latency products and requirements for accuracy. So first of all, we have the predicted orbits. We have to deliver this for Sentinel-1 with a latency of 10 minutes, which means 10 minutes after we get the latest data from the satellites or GNSS data, we have to deliver the prediction for 2 orbital revolution in the future. And the accuracy requirement is 1 meter. Then we have the near real-time orbits, which we also have to deliver within 10 minutes after getting the latest data. And this we deliver for all missions with slightly different accuracy requirements depending on the mission. So either in 3D for Sentinel-1 and 2, and for Sentinel-3 and 6 we have a radial accuracy requirement of 5 centimeters. Then we have the short-time critical, somehow related to the rapid solution, as you know it from the IGS, which we deliver for Sentinel-3. And then for the non-time critical, we do this for Sentinel-1 and 3. And Sentinel-2, we also do this, but this is just for external users, so this is not needed by the projects to deliver any data on the project side. And last but not least, we also include Sentinel-6 for these non-time critical orbits, and this is mainly for the quality control of all the orbit products that we have these non-time critical orbits here. So what is now the connection to the IGS? I think the most obvious one is, so we have the satellites with the GNSS receiver, so you can see this with these red and orange circles where they are placed on the satellite. We have, by the way, on all of them we have 2 receivers, so a main and a redundant one, but only one of them is running in operations. And so for Sentinel-1, 2, and 3 we have a GPS only receiver currently, and for Sentinel-6 we have Riley, and all future satellites which will come, we have a slightly different receiver which can track GPS and Galileo. And so we are doing the so-called PPP approach for neo-precise orbit determination, so we all do reduced dynamic orbit determination. And for this, of course, we need GPS or GNSS orbit and clock products. And there the IGS come into the game. So we are using mainly the final orbits and clock products. And since May 2020, We're also doing the ambiguity resolution with this PPP approach. And there we now use the analysis center-specific, rapid, maybe final solutions together with the provided bias products to be able to do this PPP-AR for the satellites. So, coming back to this nice icons here. So, we have these predicted near real-time and short-time critical orbits, and for these products, we cannot use the IGS products because we cannot make a contract with them or with the IGS that they really deliver us all the products. So therefore, these product lines, they have to be covered by an external GNSS product provider, and this is done also from a group at GNV, which are these GNV G-Sharp product generation. For the short-time critical, some of them, some validation products, and for the agency, there I would say we are premium users, or as Wolf called it, power users of the IGS AC orbit clock and bias products. And as I already mentioned, so for TU Delft is producing some short-time critical products for validation with Gypsy X, and this relies on the JPL rapid solution. And they also doing a test solution which even uses JPL ultra rapid solutions. So with all the groups which are either in the consortium or in the quality working group, I have listed here all of them, which provide solutions with the software packages which they use, and then also which IGS AC final solution is used. So in bold, these are really the solutions which are submitted to the IGS for the combined solution at the end. And the others, there are some exceptions, so to say. So we have for CNES, they use the GNSS solution, but this is an extra solution because CNES is until now still relying on the IGS 14, and so GNSS is delivering them an extra solution still on the IGS 14 reference frame. And for the future POE-G standards, at least to my knowledge, this will also be an extra solution, but then including the seasonal ITRF 2020 geocenter motion model. For GSZ, they also have an extra solution which they use, which is fully consistent between GNSS and LEO modeling, so really from the gravity field, ocean tides, everything together, so it's all fully consistent. And as I said, for JPL, it's not only for TU Delft, they're using the JPL solution, but not only the final one, but also the rapid and also the ultra rapid for a test solution. And last but not least, TU Graz. It's TU Graz contributed to REPRO, but not for the operational product, so therefore it's also not in bold here. But what I also want to show here is that several IGS AC solutions are used. Well, Kodi has the most contribution, but we also have the ESOC and JPL solutions which are used here. So coming to the quality control within the CPOD service. So the quality control is done in so-called regular sales reviews. We are doing 3 per year. So one is covering January to April, one May to August, and then the third one is then for the entire year before. And what is part of this is so, on one hand, so checking the latency of the products. So for the predicted orbits, the near real-time ones, and the short-time critical, also the latency is of course somehow critical. And This is done also in these regular service reviews. Of course, because of the short latency, this is also controlled, so to say, online when they have to deliver this. They also control about the latencies. But in these regular service review reports, they are also all together, compiled together, and there are made some more checks also for the short time critical products. So also the prediction and near real-time products are compared against short time critical or non-time critical products, which is in the middle here, where you can also see that, for example, so Sentinel 2, we have here a comparison to the combined orbit, the 3D RMS, and you can see we have a 3D RMS of below 10 centimeters, so, or even below 5. And for example, here for the Sentinel 6, we have also the comparison of the short time critical to the combined orbit, which is then listed in the reports. And for the short time critical products, we also compare them to the non-time critical products. So there are made a lot of cross comparisons with all the products. And last but not least, which is the main part and the most important part, I would say, the comparison of the non-time critical and these non-time critical products which come from the quality working group. They are compared to a combined orbit product. And this combined orbit, I would say, is another connection to the IGS. So, as I said, the members of the quality working group, they deliver orbit solutions for the satellites based on their software and their processing strategies to these regular service reviews. And then a weighted mean of all the orbit solutions is generated, and the combined orbit is then serving as a reference for cross comparisons. And I think this is really a great heritage also from the IGS orbit combination. As an example, you can see here on the left side for Sentinel 6, I have for 1 year these daily weights of all the contributing orbit solutions. So the higher the higher the dots, the higher the weight for these solutions. And then we also look for the consistency of the orbit solutions compared to this combined orbit solution. This is on a year where we have the radial, a long track, cross track, and 3D RMS of all solutions. And for the 2 satellite missions where we have the laser retroreflector, we also do then SLR validation, and they are also for all contributing orbit solutions. And on the very right, we have the combined orbit here. I will come in the next slides to a bit more detail on the results here. So, yeah, this regular service reviews. I have here the results for all satellites for the latest yearly report we made for the year 2023. And we have here Sentinel 1A, 2A, and 3A, and all the contributing solutions are compared to the combined solutions with radial, long, cross track, and 3D RMS. And so the scale is slightly different for the satellites. So Sentinel 1A and 2B is 1.2 centimeters here on the top, and here we have 1.4, so but not very different. But I think we can say that the 3D RMS of all contributing orbit solutions compared to the combined one is below 1 centimeter. So we have extremely high consistency between the different orbit solutions which we achieve here. And for these satellites, this is the only thing we can do. We don't have independent validation via laser. This can only be done by Sentinel 3 and Sentinel 6. But what I want to show also is what we achieved during the last years. So you have here from a very early regular service review in spring 2016, where we did not have so many contributing solutions. And here it's the comparison from all solutions to the CPOD solutions. But you can see from the scale that we have a 3D RMS there of more than 2 centimeters, so we really can see the improvement which we made during the years for the satellites. And so this is mainly due to background model updates, modeling improvements, and of course also the integer ambiguity solution which we are doing now. For the Sentinel 3 and 6, I used a slightly different graph here. So I plotted here for the daily radial RMS from all contributing orbits versus the combined one. So 3A, 3B, and 6A. The laser validation. And so here we can say that the radial RMS is between the combined and all the quality working group orbit solutions is below 1.5 centimeters, so also very high consistency between all the orbit solutions. And for these satellites we also have the laser retroreflectors, so we can independently validate this, and we do this by laser validation. And here we use 12 selected stations and estimate the station range biases based on the combined orbits of Sentinel 3A, B, and 6 together, so not from one satellite only, but from these all 3. And for most of the orbit solutions, we can see a SLR RMS between 6 and 9 millimeters, so very nice result, I would say, for orbit solutions. So coming to the next connection to the IGS, so the IGS Amtex. So we are using, of course, the IGS Amtex for the GPS+Galileo satellites, and for Sentinel 6, which is at the height of 1,300 kilometers, so very high satellite. We have the problem, which was already mentioned in previous presentations today, that we have observations which are taken beyond 14 degrees Nadir angles of the GPS satellites. So on the left-hand side you can see the histograms of the Nadir angle distribution. So it's on the left it's Galileo for the IOV and FOC satellites. So we are going up to 15, and then for GPS we have the different blocks here, and GPS 3 is the blue one. There we have, all of them go up to 17 degrees. And about 50% of all GPS 3 observations taken from Sentinel 6 are beyond these 14 degrees. And this sums up in total to 8 to 9% of all observations which the satellite tracks. And the problem here is that for the GPS3, the phase center corrections beyond the 14 degrees are not available in the IGS 20 Amtex. So you can see this here in these only Nadir independent PCBs. So these currently it's just a straight line here, just the values from 14 degrees are copied here. And if you use this, then the residuals from Sentinel 6, they are looking, just for the GPS3 satellites, they are looking like this. And in this case, now we are using the values which are published by Conrad et al. Last year, and we use them within the CPOD service, and then we get a flattening of these residuals here. And there I would like to pose a question, so if there are any plans in the IGS to routinely extend these phase center corrections for new GPS satellites as it was done for the previous block satellites, and also how we can support this from the PPP service, or also the other way, we heard this morning that there are also disclosed values for these higher Nadir angles from the GPS providers. So if how we can support to validate such values with the PPP service. So the next connection is the ITRF. So the changes in the ITRF have to be taken over automatically by the CPOD service. As soon as the IGS switches from one reference frame to the next, we have to take this over because we're just working with the IGS final solutions there. So during the run of the service, we had now 2 switches, so one from IGS 08 to IGS 14 and then to IGS 20. And so to get a consistent product series for the Sentinel satellites, we have to do also reprocessings then for the full mission time. And for Sentinel-1, we already did this in 2021. On the right-hand side, you can see some examples from the results from all groups which contributed to this. New comparisons to the new combined orbit then. And in the case of Sentinel-1, we also could, of course, remove some other model and processing setup changes which were done during the long mission time of the satellite. So, for example, here you had an antenna reference point update, orbit parameterization update, and also the switch from empty to fixed solutions. And with this reprocessing, we could get out these inconsistencies in the series. And for this reprocessing, Code kindly provided us reprocessed GPS products in the IGS 14 and the corresponding bias products. And there it's, that the CPOD service really appreciates the reprocessing campaigns within the IGS because they are of great benefit for the reprocessings which we have to do. And there also the question if there are plans to provide reprocessed IGS combined products, including the biases for ambiguity resolution from our side. Another connection to the IGS GeoCenter. So I think I do not have to go into detail, and I do not want to go into detail because this would be another keynote, I would say. Well, we have the GeoCenter motion, so the variation between center of mass with respect to center of network. And this is one of the main topics which we are discussing and which have to be handled within the Copernicus POD service, respectively in the POD quality working group. Really the modeling of the GeoCenter motion, and there are 2 issues. So one is the quality control in the regular service reviews. So because part of the Sentinel orbit solutions which you get are delivered referring to center of mass, and some are referring to center of network. And even if we harmonize them or transfer the ones to the other system, we still see in the cross comparisons not only orbit modeling and processing differences, which would be the aim to see in the comparisons, but we also see the differences in the GeoCenter motion modeling. And you can see, for example, here for Sentinel-6, I have put here for the radial RMS and also the 3D RMS, you can see some signatures in some of the solutions, and these are really can be related to different GeoCenter motion modelings. And the second point here is that the GeoCenter motion modeling in the LEO POD processing itself. So also there the ITF 2020 recommendation to use this new ITF 2020 GeoCenter seasonal model versus the realization which how it is done currently in the IGS. And so there is also the question about the future strategy in the IGS regarding this GeoCenter motion modeling. Future missions is also a connection to the IGS. So the PODRIX receiver, which is currently on the Sentinel-6 Michael Freilich satellite, and then coming on all the future Sentinel-1, 2, 3 CD satellites, and also Sentinel-6B, is able to track GPS L1 and L5. The current tracking scheme, besides Galileo, is L1 and L2 2Y for the older GPS+R satellites, and L1 and L2C for the 2RM, 2F, and 3 satellites. So currently there is no need, respectively, no plan to switch to GPS L1 and L5, but as soon as the entire GPS constellation is capable to transmit the L5, the question will arise whether L5 should be tracked instead of L2. So this question will come to us as PPP service. Would you like to have L1 and L5 on the satellites? And at least one of the future Copernicus expansion missions, so ROSE-L, where you can also see this picture here, will only be able to track L1 and L5 and no longer any L2. And so there's the questions, are there plans to extend or expand the IGS product series to GPS L1 and L5 compatible products? Okay, so already summary of this part. So as I said, so the Copernicus PPP service is a premium user of IGS products for precise orbit determination of the Copernicus Sentinel satellites. The Copernicus PPP service very much appreciate the enormous effort and work put into the continuity, quality, and enhancements of the IGS products. We also benefit from this, of course. And I think I could show that the connections between the IGS and the CPOD service are manifold. I probably forgot also some connections which might come to your mind. So the CPOD service greatly benefits from the IGS, but I think we can also support the IGS in its enhancements. And I would be very happy if we could get connected through this. And before closing, I would like to say some words about the future for the Copernicus Sentinel satellites. So going mission by mission, so Sentinel-1, as you have seen, we have only one satellite left, so Sentinel-1A, which is the oldest one, more than 10 years in orbit now. It had some anomalies, so it's no longer the very healthy satellite, so it's really getting old. And Sentinel-1B had to be dismissed already 2 years ago, 3 years ago. And so the next Sentinel-1C is planned for end of November. But this is pending successful degas firing test. So, but we hope for the best, and in 2025 we hopefully have them again. Also then Sentinel-1D. Sentinel-1, Sentinel-2. So this is the very next satellite which will come, Sentinel-2C, in the beginning of September. This launch is planned. And here we have, after the launch, the current baseline is that they only operate 2 of the satellites, so we will see which one, probably Sentinel-1A, 2A will be taken out. But we hope that we still get the GNSS data to work with them for the PPP. Sentinel-3, here is listed the overall status of the mission. The very last point here is the one which is important for the future. So Q3 2026 is the current plan for the launch of the C satellite, and D is then coming later than 2028. But both of them, they are already in storage, the satellites. And last but not least, Sentinel-6. There we have a planned launch November next year. And then after drifting phase and tandem phase with Sentinel-6A, we have hopefully in November 2026 a new altimeter reference mission, which is then Sentinel-6B. Okay, Copernicus expansion, I already mentioned ROSE-L. So there we have a lot of expansion missions here. I cannot tell you more than what is on the slide here on them. Only that ROSE-L crystal, they also require precise orbits. So they are also need a precise orbit determination, and yeah, we hope, of course, that you can contribute to them as well. And that's the end of my presentation. Thank you for your attention.
Thank you, Heike, for this nice overview. Are there questions?
Yeah, I'll quick just point out. I think JPL is now
please use the mic. We have the people also the breakout.
Yeah, just a point of order. JPL is now using GCX to create its Sentinel 3 and Sentinel 6 orbit clock products, not GNSS.
Okay.
And also, Alex Conrad just wrote a new paper in which he compares the Sentinel 6 POD, the trick receiver versus the project receiver, GPS only Galileo, and GPS and Galileo. And that's an interesting paper on like how well we do the Sentinel 6 POD.
I know about it, thank you, yes.
Just a very stupid question. Is this a Copernicus PPP service or is it a Copernicus accurate orbit determination service?
What is a POE or POE?
POE stands for precise orbit determination. Do you aim at accurate orbit determination?
We would like, of course, but
Unfair, but
we would like, of course, but for some satellites, it's of course difficult to get the accuracy. Well, you know it.
It sounds already philosophical. Okay, come on.
Yeah, also question for the Sentinel 6. We have observed that in the GPS observations of Sentinel 6, there are rapid switching of GPS observations between different channels. Is there any reason for this? And is there any possibility that this could be fixed somehow?
There, I think you asked the wrong person. Well, we have not discovered this, but anyway, interesting discovery. Would have to look into this, so, but I cannot tell you if there is a reason for this.
Okay, then I think it's the point to move on to the poster session, but I should not forget to thank Heike for this presentation with something special from Bern.
Thank
And
you
of
very
course,
much.
prepared specifically for this event.
Thank you.